Hi, and welcome to Lesson 6 in our unit on the nucleus. Here we're going to talk about artificial transmutation. And so I thought I'd start this discussion by showing you one of the most amazing machines that humans have ever built. This is called the Relativistic Heavy Ion Collider. You can see it on the top of this map. It's huge. It's a particle accelerator, but it is by no means the biggest particle accelerator that we have created. The largest particle accelerator currently is the Large Hadron Collider, which is run by CERN on the border of Switzerland and France in the Alps. Let's go in and take a look at these particle accelerators, how they work, and what we want to do with them. So, artificial transmutation is the production of radioactive isotopes by humans. This is accomplished by smashing atoms and particles together at very high speeds. If you remember back to our discussions about the nucleus, there's a tremendous amount of positive charge in the center of that nucleus. If you want to smash two atoms together, you need to overcome those forces. And so you need to get these particles traveling at very high speeds in order to get it to happen. In order to do that, you're going to use a particle accelerator. So this is a view inside of the Large Hadron Collider at CERN, and what you can see is it's just a giant tube. This is the maintenance tube. This isn't the tube that the particles go in. This is what CERN actually looks like by air. So you can see that it is a huge ring, and in that ring is where the particles travel that you're going to smash together. Artificial transmutation was not always done in these giant structures. The first forms of artificial transmutation were actually discovered accidentally in the lab in the early part of the 20th century. But as scientists wanted to create larger and larger atoms, you needed to smash particles together with more and more force. And that's one of the major reasons why particle accelerators have been developed, though certainly not the only reason. You're going to need to be able to recognize an artificial transmutation problem and solve it to determine the identities of missing isotopes. This example is from page 15 in our packets. If you look at it, you can see that it's a little bit different than the natural decays that we've talked about up to this point. The major difference that I can see from my end is that you've got two reactants, in this case californium or CF and carbon. This is representing the notion that in an artificial transmutation, you're going to smash these two isotopes together to produce something new, which we're representing here as X. Also notice that other particles are produced. In this case, it's a neutron, and actually there's 4 neutrons. So as shorthand, rather than writing the symbol for a neutron 4 times, we just write a 4 in front of the symbol for a neutron. What I'd like you to do is determine the identity of this missing nuclide X. Pause the video, take a moment, and see if you can solve it. And then when you're ready, play through and let's see how you did. So it's still just a matter of math. Let's look at the mass and the atomic number of the isotopes on the left side of our arrow, what we might call the reactants. 249 plus 12 is 261, and 98 plus 6 is 104. We know that that total mass and total atomic number has to be represented in the particles on the left of our arrow, or what we might call the products. We don't know what X is, but we do know that we've got 4 neutrons. Each neutron has a mass of 1, so that's going to be a total mass of 4, and each neutron is not a proton, so that's going to have 0 protons. Once we figured all of that out, we have all the information that we need to figure out what X is. X has to have a mass equal to 261 minus 4, or 257. And X's atomic number has to be 104 minus 0, or 104. If we go to the periodic table and look up element number 104, we get the symbol RF, or Rutherfordium, named after Ernest Rutherford, who you may remember from our first discussion of this unit as the discoverer of the proton, and who did a lot of other things. He was actually on hand for the first accidental artificial transmutation that happened in a laboratory. On page 15 of your packet, you have a chart that compares natural decay, or natural transmutation, and artificial transmutation. I think that this is a really great chart, and I'm going to spotlight it here because it's a really great way to think about these kinds of processes by considering their similarities and their differences. We're not going to take the time to go through this chart right now because you have access to it, but I would definitely encourage you to go and look at this chart when you have a moment in order to get a handle on the similarities and differences between natural decay and artificial transmutation. Thanks so much for watching our discussion of artificial transmutation. Make sure that you can do the following here at the end of this video. Make sure that you can identify an artificial transmutation reaction by looking at it. If I give you one, you should be able to identify it just by eyeball, that it is in fact artificial transmutation and not natural decay, for instance. Also make sure that you can determine the identity of unknown nuclides in an artificial transmutation reaction, just like we did to figure out that it was rutherfordium. Can you solve any artificial transmutation with a missing nuclide to figure out what its identity is? And finally, make sure that you can explain how artificial transmutation reactions are similar to and different from natural transmutation reactions. If you can do all of these things, then you're doing great. If not, that's okay too. Take a moment, write down any questions that you have. You can always leave them in the comments below the video, and you can always get in touch with me through the information below the video. Thanks again for watching. I really appreciate it. Have a great day.